Welcome to Automated Visual Software Analytics. This part is about the software map theme Technical Debts. In this part, we will briefly outline characteristics of the phenomenon of technical debts. We will explain software maps that depict technical debts, and we will discuss their application and some actionable insights that can be gained by this kind of software map. Let's start with the phenomenon of technical debts. Technical debt is a debt that accrues when you knowingly or unknowingly make wrong or non-optimal design decisions. So this is one way to describe technical debts in software engineering. This expression was coined originally by Ward Cunningham and describes technical debts as something that is introduced whenever developers choose to have a quick or ad hoc implementation rather than a well-designed implementation. If it is a quick or ad hoc implementation, then the accrued interests, virtual interests, accumulate somehow, similar to financial debts. One way to resolve technical debts is to apply, for example, refactoring as a general way to reduce technical debts in the long run. So, technical debts aggravate program comprehension in general, they increase the risk of introducing bugs in the code, and they decrease any precision of all kinds of estimations, and they have much more negative effects. So technical debts is a very interesting phenomenon in software engineering. It's described by this metaphor of the financial world, but especially during software maintenance, it's a key phenomenon that affects software engineering in general. So we can ask, how can we express this phenomenon? How can we make visible this phenomenon by means of software maps in the context of software analytics? This is an example of a software map that depicts technical debts. It's part of a Java-based system, namely the Android operating system, or part of it, and we apply the logical lines of code as a footprint size. We use McCabe complexity as the height of the cuboids, and this is correlated by a color scheme derived from the nesting level complexity. So basically, the software map that depicts technical debts is one that shows size of modules and the correlation of two software complexities, for example, McCabe and nesting level. To get more details here, as already said, the logical lines of code mapped to the footprint size used to expose monolithic code as a first indicator to code that is hard to manage. McCabe complexity, which is mapped to the height of the cuboids, is used to indicate complex, error-prone code or codings, focusing on the control flow complexity. And the other dimension we include in our map representation is a nesting level metric, mapped to the color, as an indicator for software complexity that focuses on the complexity due to the depth of logical nesting. So by combining these two technical measures of software complexity, we can at least estimate the degree, or let's say the general volume of technical debts behind our current implementation, behind the software systems, source code, modules and units. The composition also uses a combination, and this combination, in our case McCabe and nesting level, guides somehow the awareness of the observer, of the user, of the expert towards modules that are highly affected by both software complexity indicators. High nesting level complexity is experienced as a stronger productivity train than compared to McCabe complexity, and for that reason we use color as a kind of prioritization function for complexity hotspots. This is why we map nesting level onto the color visual variable. Where both high McCabe complexity and high nesting level measures meet, program comprehension is severely aggravated, and hence it is most likely that those modules contain a lot of technical debts. Typical use cases and applications of this software map theme includes the following. Technical debts can be identified by this kind of software map. It highlights those source code units that most likely will have a lot of technical debts, estimated by the correlated McCabe complexity and the nesting level complexity. We can also focus software development activities on highly technical debts code to reduce implied future costs due to technical debts. We can precisely apply code refactoring to those modules in order to reduce complexity as an investment, as a kind of investment in the future maintainability of the code and hence the overall system. Potential conclusions and way of proceeding includes that we first should try to reduce the nesting level, measures the nesting level complexity in affected modules that show high technical debts, and then try to reduce McCabe complexity. This is a rule of thumb, and here once again we are in the scope of prescriptive software analytics. Let's summarize these findings about the software map theme technical debts. It can be applied to reveal and monitor the so-called technical debts inherent to a software system's implementation, and it's inherent to all software systems implementations. Technical debts is among the strongest factors that influence the long-term development and its cost. As a starting point for exploring technical debts, McCabe complexity correlated with nesting level measures are commonly a good first estimate of the technical debts. Of course, we can include, according to the type and nature of your specific project, we can include more or different metrics or other indicators that help to fine-tune the estimation of technical debts. While reducing, for example, the lines of code having a nesting level 4+ complexity even to 0 without an impact on feature completeness, one cannot generally reduce McCabe complexity in the same manner. If so, the functionality would have to be reduced. That is, the technical debts can be reduced to a certain lower bound that is determined by the complexity of the software system, of the complexity of the specific module, of its algorithms, and other aspects of its structure, type, and nature. With software maps that show technical debts, however, we can easily and directly identify and then monitor and observe those modules that are estimated to have a high degree of technical debts. This concludes the part about the map theme technical debts.